Okay, so welcome everyone. Welcome to Physics by Aryan. I am Aryan Mehra and I am taking the lecture series on quantum mechanics in three dimensions. Today is the third session, and before I jump into third session, I very quickly want to recap what we did in last two sessions. So in the first session, we basically discuss about how to think in terms of quantum mechanics and what are the states in quantum mechanics, what are the eigenvalues, what are the operators and so on. Okay. Then in the second lecture, we actually began studying the quantum mechanics in three dimensions. What we started doing is we started doing hydrogen atom. So if you know hydrogen atom very well, then most of your quantum mechanics in three dimensions is done. In hydrogen atom, we know we define all the physical parameters, for example, energy, radius, angular momentum, and so on, in terms of three quantum numbers, which are N, L, and ML. Okay. Now in our quantum mechanical theory, how these three comes into play that we discussed. Okay. Now the main thing which we focused upon was that we want to solve our Schrodinger equation for quantum mechanics for hydrogen atom. Okay. And we all know time independent Schrodinger equation is something like this. Okay. The solution of the Schrodinger equation, this is a very important point. The solution of the Schrodinger equation gives you the energy eigenstates. Energy eigenstates. Okay, or you can say eigenstates of operator Hamiltonian H cap. What do you mean by energy eigenstates? It simply means that let's say your hydrogen atom, you are measuring the energy of an hydrogen atom and you find out that energy is E1. Then you say your hydrogen atom is in state phi 1. Okay. And if its energy is E2, it is in state phi 2. Okay. If it is E7, the state is E7. Something like that. So the state which you write when you have energy E1, that is called energy eigenstate. Okay, if you write states corresponding to momentum, for example, let's say if you're saying I am not measuring energy, I'm measuring momentum. So if I get P1, I will write state phi 1. If I get P6, I will get phi 6. So these phi 1, phi 6 will be the momentum eigenstates. Similarly, you can define any eigenstates, every operator, or you can say every physical observable is represented by an operator in quantum mechanics, and every operator has eigenstates. So when I say you find the state, you just simply find the energy eigenstate. But you should know in quantum mechanics, if you know energy eigenstates, then from these energy eigenstates only, you can also find momentum. You do not need to differently again find momentum eigenstates. Why? Because in classical mechanics, you remember, if you know acceleration velocity by doing some mathematical analysis, just integrate it. Similarly, in quantum mechanics, if you know energy eigenstates, have heard is which is called momentum space in quantum mechanics. If you do quantum mechanics in that space, then you get momentum eigenstates. Okay, so this is something very simple you should know conceptually. So we started finding these energy eigenstates. I didn't went into the detailed derivation that how you can actually solve the problem and so on. But the very first thing which we saw is our potential is radially symmetric. Okay, radially symmetric in hydrogen atom. This is your potential. It represents that your potential only depends upon r. It means everywhere on the surface with radius r, your potential will be same. So your system should have some sort of symmetry, which is radial symmetry. So you should work in spherical polar coordinate system. So we started working in spherical polar coordinate system. So we said our energy eigenstates will be the function of r, theta and phi. Okay. Now in quantum mechanics, there is one very basic technique that you can actually separate the variable. So we said our total solution will be the product of three solutions. Okay. Product of three functions. One function is a function of r, another is a function of theta, and another is a function of phi. Or we can also write it as theta phi. Okay. Here y is we discuss is called spherical harmonics, and r is a radial part of the solution. So we discussed everything about the spherical harmonics, which is y part. That if I give you some y, how you can actually find the quantum numbers. So in y there are two quantum numbers hidden. One is L and another is ML. And in R there is a quantum number hidden, which is N. So we discuss about quantum number L and ML. And if I give you any spherical harmonics, how to plot that and how you can actually find L and ML from this. Today we will discuss how to actually not actually derive R part or radial solution, but how to actually analyze the radial part of the solution. We only want to analyze. We don't want to derive it, because in no competitive exam they ever ask you to derive. They will give you some radial solution, and then based on that you need to find the different physical quantities, or you need to do many things. So let's discuss that. Okay. Okay, so let's begin. So radial solution. If you actually solve the, if you actually write the Schrodinger equation and only keep the part of the equation which only contains r, then your equation will somewhat look like this. You don't have to memorize this or something. If you want, this is a very simple equation. You can even memorize it. There is not a very big problem. It's simply minus h cut square by 2m d square u by dr square. Now what is u here? U is a new parameter which has defined. U is r multiplied by capital R. What is capital R? R is a radial part of the solution. And what is small r? It is simply the distance from the origin, that you know in spherical polar coordinates what is small r, plus v plus h cut square by 2m L by L plus 1 by r square, then again u. It is very similar to Schrodinger equation. The only thing which is different is there is then extra term which is L by L plus 1 term. Now what is this extra term? Everything else is same. Only this part is called centrifugal term. This comes because when you are actually in rotation, there is some sort of, I am not saying in quantum mechanics exact centrifugal force. This is the exact centrifugal force, but this is a analogy to the centrifugal force. Just like in quantum mechanics there is a centrifugal force, here also it is there. So this entire v plus h cut square by 2m L by L plus 1 by r square is called effective potential. You don't have to much worry about that, but you should know how these things are actually evolving. So this is called effective potential, and one part of it is called centrifugal term, and another part is called V, which is due to the force acting on the systems. Okay, because F equals to gradient of V. So V representing what are the forces which are acting on the system. And L by L plus 1 term is a centrifugal term. Okay, this is because in which your system itself is in some sort of rotation, not exactly rotation, but analog to rotation. So because of that, you have some inherent force, which is centrifugal force. So that's all it want to say. Now, the solution of this equation, if you see, will depend upon what is the value of your potential. Okay, this is a general Schrodinger equation, general radial part of the Schrodinger equation. You can use it to solve any problem, but now here we are solving hydrogen atom. So for hydrogen atom, you know, potential is minus ke square by r. So if you put that in your radial solution and actually find the solution, then you find that your solutions are coming in terms of Lagrange polynomials. Again, no need to worry what are Lagrange polynomials, and so you only need to worry that when you put this, then your equation becomes something which only can be solved in terms of special functions. So do you all heard about special functions? Can you name few special functions? Let's name it.
Yes, sir.
What special functions have you heard? Yeah, tell me.
Bessel
Bessel
function,
solution,
Bessel function, legendre,
Laguerre polynomials,
Legendre polynomials, Bessel's, what else?
legendre,
Fourier
Legendre,
series,
what
Fourier
else?
transform.
So Fourier series, Fourier transform is not special function. Bessel,
Hermitian,
Legendre, Legendre, what
Hermite
else?
polynomial,
Huh?
Laguerre polynomial,
Yeah, Legendre polynomial. What
Hermite,
else?
Hermite polynomials.
Hermite
Harmonic.
polynomial.
Okay, so now tell me where you heard Bessel functions. Which problem, if you solve, comes out in terms of Bessel functions? This much you should know. These are the questions which are asked in the interviews. You don't have to actually drive it, but you should know where Bessel
In
functions come.
hydrogen atom,
Sir,
we use
in
Bessel
central
functions, most
potential
probably.
problem, we have deal with
No, in
uh,
hydrogen atom, Bessel function does not come. What Ashwin is saying? Yes.
the central potential problem.
Central potential, no. In central potential, Bessel will not come. So you remember that Fraunhofer optics?
Yes.
In that you solve Bessel functions. In that Bessel functions comes into play when you are actually solving light falling on the disk. Your solutions are Bessel functions. Where okay, now tell me, we already discussed where Legendre polynomial comes. We already discussed this in last lecture. Legendre polynomials are
Angular
told.
momentum.
Yeah, so your spherical harmonics comes out in terms of Legendre polynomials. Okay, and now where Lagore are coming? Lagore are your radial part of the solution in hydrogen atom. Quantum mechanically comes out in terms of Lagore polynomials. I will give you a very basic homework that please write all the special functions which are there, at least 5 6, and then you also should know that where they come. You don't have to drive it or something, but at least 2 3 problems you should know in physics where they comes. Okay, that will be very beneficial in your career. Yes, Bharat, do you have any question to ask?
Sir, actually, I'm not able to see your screen, sir.
How many of you are not? Everyone else can see my screen.
Yes, sir.
Bharat, do one thing, leave the meeting and join again.
Yeah, sir, I
Okay.
did that actually.
I don't know how to solve this problem.
Sir, is it
The only,
important to know all these solution of the of these polynomial also?
No, you don't need to know anything about this. You only need to know where they come. That's it. That's everything. Anything. Okay. So now we don't care what these our radial part solutions, how to drive them or what they how to do them. Like we only want to know if I have a solution, how to play with that, because this is what you need. So you will see that your solutions in hydrogen atom will look something like some coefficient A. Okay, this coefficient A is not, do not need to be constant, not constant. Okay, not constant, or I should write it like A function of R. It can be a function of R as well. Do not need to be a constant. Okay, into e raised per minus R by NA. R by NA, where N is a quantum number which we are discussing from the class 11th and 12th. Now here I haven't written, but I want to ask, I have mentioned that in quantum mechanics, quantum numbers comes because of the boundary condition. So because of which boundary condition this N quantum number comes, or yeah, that you need to answer. Take a guess. When was the first time that you heard N?
For energy.
No, energy in energy formula, but is there any condition, boundary condition for N in energy? So this quantization comes, okay, Bohr gave the quantization that angular momentum must be quantized. So they give the quantization rules, but quantization must come from some sort of boundary condition, and this boundary condition must be in R. Okay, because of the small r, because for small theta we already got a boundary condition L, for phi we got an boundary for quantum number ml. What is the boundary condition here which is giving us small n? Can
Kx
you
is
think
equal
of,
to n pi.
can you repeat what is equals to?
Kx.
K, kx equals to n pi. Okay, or maybe kr equals to n pi. Why this boundary condition need to be satisfied? Any vague idea? Okay, so this is an open challenge for you. This is an open challenge. I won't answer this question today. Let's see who can answer this question for the first time very accurately, because you will not find this answer in any book. Not your, it's not possible that you can find it in any book. This you have to think. And let's see who can think how much. So tomorrow in the class I will discuss from where, from due to which boundary condition this n is coming, and then we will discuss more about it. Okay, so now for now let's move on. Yeah, Bharat, you want to take?
I think this n is coming from the boundary condition x is equal to a and x is equal to 0. So when we
No,
put
it's not an infinite potential well where it is confined between 0 and a. It's an hydrogen atom. Your
okay, yeah,
R can, yeah.
okay, okay,
So that you have to
okay.
think. So now if I give you the radial functions, these are few of the radial functions R and L. So you know if n is 1, L can be 0. So for R10, just by looking at the solution, you can see that it is e raised to minus r by a. It means n is 1. Okay. In this you can see minus r by 2a. It means n is 2. In 2, 1 again n is 2, and so on. So can you see that how it is evolving? Okay. By looking at any solution, can you simply tell what is n now? It's a very simple task. Is it clear to everyone? How you find n?
Yes,
Just
sir.
by looking. If I hide this, you can easily find n. Now my question to you is, can you find L by looking at these solutions?
We need sine and cosine terms.
Yes, one is that, but sine and cosine in which? Spherical harmonics. Here I have only given you radial part of the solution. So sine theta can't come in this. So how you actually find, because it is written R and L, it means it has an information of L, right? So how do we find, how we found that? Okay, let's say I found that n is 2, but what, n 2 0 or 2 1? How do I find that information? So that information is actually contained in the number of nodes. So if you don't know nodes, here A is called Bohr radius. So what is Bohr radius? It's a minimum radius. Can you give me the value of this Bohr radius? Very simple. You all have heard in class 11, 12.
0.53 angstrom.
Yes. So all agree with the Sahin? Is it 0.53 Armstrong? Hmm? No one else has an opinion about it. It's very simple, 0.53
Yes.
Armstrong. Yeah. So this is a minimum radius in an, you can't have a orbit below that. In Bohr theory. Bohr theory talked of discrete orbits. After this, all three solutions are done, I will actually give you what quantum mechanical picture of hydrogen atom looks like. It's a very complete different picture than what you have done in Bohr atom. Okay, so now let's move on. So number of radial nodes. Number one thing you should know, radial nodes. Radial nodes means the nodes in radial part of the solution only. You don't have to consider y and only r part of the solution. How many nodes? Nodes is a term used at how many points your r goes to 0 when it is plotted against small r. Okay, capital R versus R graph if you plot, that at how many places it goes to 0. So this, if you can see this circle I have drawn on the graph, this is actually giving you the node. This is actually giving you the node. So the formula for nodes, which you don't need to actually worry how it comes on, how the derivation is, the general formula for nodes is n minus L minus 1. Okay. So if I give you R1 0, how many nodes you think will be there? So n is 1, L is 0, and then again minus 1. So number of nodes will be 0. So in R2 0, if you see, number of nodes will be 1. In R2 1, number of nodes will be 0. So now if you have R2 0, let's say, or I give you a function from e raised to power minus r by 2a, you can say it is n equals to 2. Very simple. Then you plot both of these functions and see how many nodes are there. From that you will get an information about L. If there is no node, then is it L equals to 0 or L equals to 1? If there is no node, 1. Okay, because it's clearly written, if there is no node, then it means it is L equals to 1 if n is 2. Okay, so if you see the graphs also, it quite matches with that, because R10 has, if you see the plot, there is no node in that. If you see R21, again no node. Node means in between 0 and infinity there should be a node. You can't consider a node at 0. You can't consider a node at infinity. In between that there should be a node. But if you see R20, there is a node. There is a node, and I have highlighted that. So very simple. Everyone understood till here? Very simple theory.
Sir, is it related to some kind of probability, this radial node?
Yes, nodes are always related with probability. See, your wave function, if you take its complex conjugate into this, means if you find its what is a square integrable, if you do it square integrable or square it, then you get a probability. So if your r is going somewhere 0, it means your probability there is also going to be 0. So it means you cannot find your particle at the node position. Means at this r value, you will not have the what do you say, your particle. Can you actually imagine in terms of quantum mechanical theory how it is going like this? Why it is happening? R10. We will actually discuss it how it is going. So let's try to imagine how these R are actually looking in this picture. Let's try to imagine it. Before we start imagining it, I just want to conclude 2 points. Then you will have a better understanding how to actually imagine the atom now. It will completely change your mindset. How you actually imagine hydrogen atom will actually is going to change. So now total solution, again we come back to product RNL multiply by y. Okay, so radial part multiply by spherical part will give you the total energy eigenstates, and energy eigenstates are defined in terms of 3 quantum numbers L, L, N, L and ML, which you should remember. Okay, so before we start imagining, there is only one thing which I want to mention. What is probability density in quantum mechanics? Can you tell me? What is probability density?
Sir, psi star into psi, mathematically.
Yeah, mathematically R star into 5 star into 5. But what does it physically mean? Probability density.
Sir, it's mean that finding a particle have the most probable in this
No,
particular region.
I'm not saying most probable. I'm saying probability density. It means at each point you are defining some probability. That 5 is this, at this R is this. It is called density, probability density. At each point in the space you have given probability of your particle to be there. So now can you, when we were in class 11th, class 12th, first time when we heard about Schrodinger equation and so was in hydrogen atom in chemistry. There we were being told that spherical shells, okay, dumbbell shells and so on. Now, when you define a probability at each point, then you get some sort of cloud. What is that cloud representing? Cloud is representing the combination of all the points. Yes, and all the points have some probability assigned on them. So if you actually plot probability versus your r or theta or space, any space parameter, then you start getting clouds. So for some shells, like for example n equals to 1 and l equals to 0, okay, n equals to 1 and l equals to 0. If you remember, can you tell me what will be the shape of the cloud? Very symmetric. L equals to 0 are sphericals. You remember, L equals to 0 are spherical. S orbital.
Yes, sir.
L equals to 0 means S orbital. So S orbital is spherical. So does our theory actually connects that? Now let's see the function. Let's see the function. So it is quite difficult to see just from the function that is it or is it not. But I would recommend, if you actually go and find the probability function, okay, you take the total solution, both radial part and your spherical harmonic part, and then find the probability density. How you find the probability density mathematically? You take the conjugate and take it itself and do the multiplication. That will give you the probability density. And then when you plot it with space parameter, you start getting the clouds. So for n equals to 1, l equals to 0, if you will do with these functions, you will see you are getting a spherical cloud. For p, you remember it is dumbbell. For d, you know it's double dumbbell, and all sort of shapes start getting emerging, which is not our concern in for competitive exams, but this is how it connects. So what if I say, let's say if I say our clouds, actually what rains, what is inside those clouds? Can anyone tell? When it rains, what is inside that clouds?
Vapor.
Water. Simple answer is water in any form. Yeah, water in any form, na? Then it rains. If I ask you what are those s orbitals, p orbitals, those shapes, spherical shape, dumbbell shape, okay, double dumbbell shape, what are inside these clouds?
Electrons or charges.
So yeah, so these actually represents probabilities. So if this is a shape, then electron is somewhere in between. It is not here, it is not here, it is in this, and it is not here in between center, because it is 0 here. Okay, if I draw a graph like this, it is 0. So electron can never be here. It is either in upper lobe or lower lobe. These things you have heard, na? Now in between it, now it is an orbital for just one electron. So one electron is spread over entire region. Okay, it's not actually spread. No one knows it is actually spread or not, but the probability at any time to find it is something like this shell. Something like this shell. It has some probability to find in upper lobe. It has some probability in finding lower lobe. Now lower lobe has so many points. It has probability to find it here, or here. So probability are plotted against the space parameters, and it is coming out to be like this shape. Now some people like to think that electron is spread in this shape all over the atom. It's up to your interpretation, how you interpret it. I never think that electron is in entire region spread over. One electron is broken into many pieces and something like this. It's up to your interpretation. No interpretation is correct or wrong. But the actual reality is the shells represents probability versus space parameter. That's the entire thing which is being told in this. Okay, so if you see in d orbital, there are 4 lobes. In center there is no probability. Electron can be in any of these 4 lobes. and within the lobe it can be at any of the point. Every point has different probabilities which are being plotted, and we are getting these kind of shapes. Now can you imagine, can you even for a moment imagine Bohr atom, the one n equals to 1 ring, n equals to 2 ring, all of that information is broken now. It's a new picture of an electron. How electron is inside, we don't have any idea. We can only tell what is its probability of finding at different spots. That's all you can say. Okay, so this is Pz. If you find Px, it will be like this. Okay, and Py in will be in y direction. So this is how you should actually imagine hydrogen atom if you really want to do in quantum mechanics. The moment you shift to atomic physics, I would recommend you to always trust Bohr model. Bohr model is very nice model to actually describe the atomic physics. But if you actually want to do the quantum mechanics, never imagine Bohr model. It's very wrong model. Always think in terms of electron is being spread. How one electron breaks into 1 lakh pieces and spreads all over the space, it's some other question. Is it doing like that or not? It's a separate question. Now, one more very interesting fact about is, let's say your electron is in p state and somewhere here. Now there are two questions. Number one, when you measure it, do you measure some electron here, some electron here, some electron here, some electron here, or do you measure the complete one electron at any one spot? What does actually happens in quantum mechanics? What do you think?
Sir, a single electron
Sir,
at
in
any
quantum
spot.
mechanics,
Okay. Shaheen said we will only find single electron at any one place. Okay, what else? Who thinks that if I do a measurement, I will find 10% of electron at one place, 5% at some other place, 1% at other place? But who thinks that? Or maybe third case. Any opinions? So how many of you agree with Shaheen? Tell me. Or you are not getting any idea what is happening. If you are not, do not speak, I will think that you are not getting what is happening. Yeah, speak up very quick so that we can move on. What is happening? Tell me.
Yes, sir, same as sign.
No opinions at all. Yeah, Madhu, what do you think?
Sir, I don't understand this.
So okay, good. So what I'm asking is, electron is being spread over the entire in this kind of dumbbell shape. If you find the probability of electron to be at some place and then plot it against the space parameter, like for example xyz, you will get some this kind of image that electron is somewhere here. There is no probability it is outside or outside. It is within this shape. So each point is actually presenting probability of being of electron being there. So electron is some sort of, you can think, is spread over this entire space, this dumbbell shape. Now when I measure the electron, do I find the entire electron at one place? Let's say I measured and I found that electron is here. Okay, why then I am finding electron is here if it is spread all over the space? If its probability of being is all over the space, then why I'm finding it here? Or I find 1% electron is here, 1% is here, 1% is here, 1% is here, which make more sense because it is actually spread over. What do you think is the case? Case 1 or case 2? How many of you
case
say
one.
case 1? Yeah. Who else says case 1? Yeah, tell me. Case 1.
Yeah.
So G says case 1. Anyone else?
According to
Fine. Huh?
Case, it would be case two.
article,
Okay.
Because measurement disturb the system.
we think
Okay, measurement disturb the system. Okay. How many of you case 2? Let's see how many brave faces are there in the audience. Anyone says case 2? It makes more sense.
Sir, case two. Might be case two.
Case 2. Okay. So now let's answer this. Now let's say you are a captain of Indian cricket team and you are going for a coin toss. There is a 50% probability that you will get head, 50% of probability that you will get tail. When you will actually measure it, will you get both or you will only get one?
One.
So that's what's happening in quantum mechanics. I don't know why people say quantum mechanics is very strange. This is exactly what should happen. We should only get one answer. Maybe the probability of getting everything is different and there are so many possibilities, but ultimately we will get one thing. That's how reality works. Okay, so when we will measure the electron, we will find electron to be at one place. But what is then how the probability is coming into picture? The probability is coming into picture like next time when you will find the electron, it's not sure that you will again find it here. You will may find somewhere here. So if the probability of finding electron here is 10% and here is 1%, and if you are doing 100 experiments, 10 times you will find here and 1 time you will find here. Just like a simple probability theory, this works. In coin toss, what happen? If you go for 10 coin tosses, 5 times you will see head, 5 times tails. The same thing is happening here. In a single measurement, you will find electron at one place only. But each time that place will change. And which place will come the most will depend upon which place has the highest probability. Now I want you to actually imagine these shapes very more comfortably. Okay, so this is a probability versus space parameter graph. What do you think is the probability here at this point?
0.
At the center,
Yes,
0.
0, because it is P versus space parameter graph and P is 0 here. So you will never find an electron here. Never. How doesn't matter how many measurements you do. Now there is one thing which you should always think. What is the probability here at the bottom? Is it negative?
Sir, 1/2.
No. Here, if I see the P graph, is it negative then? If this is 0, then this should be negative.
No, sir.
No, probability can never be negativeness.
Yeah. So this graph is actually wrong. Okay, this graph is actually wrong. This is actually R versus S, which is being plotted. S is a space parameter. Okay. When you actually find P, you do the R square. So this lobe will also go up. So in P versus S graph, you will see two lobes both up. Do you see why? If there is one line up, one line down, and if I do the square, then both lines will be up. Everyone understood? If one value is 3, one is minus 3, and if I do the square, both will become 9. Both will become 9.
Yes, sir.
So if I give you R versus S graph, the probability of being at the top and being at the bottom is same, because probability will be ultimately be founded by using the square. We will actually be squaring before we are actually finding the probability. So that you should always remember. If R is being negative at some place, it does not mean that its probability will be less. Minus 3 and plus 3 will give you the same probability value, because they both are going to get squared when you are finding probability. If you are finding it little hard to understand what is probability density or so, I will again recommend you to watch the previous sessions where I have discussed the basics of quantum mechanics. Okay, I have uploaded those lectures where you will actually start from the very scrap that what is probability density, what is wave function and so on, and do you have done mathematical, because quantum mechanics in 3D is a third step of quantum mechanics. First you do basics of quantum mechanics, then quantum mechanics in 1 dimension, and then quantum mechanics in 3rd dimension. It's actually an MSc topic. Okay, so now let's move on. If you
Sir,
have now yeah, yes Ashwin.
sir, in the case of double dumbbell cases, the squaring also works on that too.
Yes, in every case squaring works. Na? This is dumbbell case. Okay. So this point and this point and this point and this point, all the 4 edges are same. They are representing the same probability. Okay.
Okay, sir.
Because these two will go up. Okay. So that's something that is okay. So now let's move on. So here I have given the definition of radial probability density. Only radial probability density. I am not talking about the entire wave function. Because radial probability density and spherical harmonic probability density both can be defined separately, or maybe there is no problem with that, but here we are only taking radial part of the solutions. What does it tell you? It tells you the probability of finding a particle at different values of r in a shell. Shell here is a word which we are being using for hydrogen atom from very lower standard classes. Okay, now if I give you r10 and if I ask you to find the probability density dp, what does this dp means? Dp means what is the probability that I will find an electron in the volume dv, in the small volume dv. This is how we do the mathematics. If you want to find a probability density at all the points, you will say dv approaches to 0, means your volume, small volume, is almost 0. Okay, almost 0. But dp means what is the probability of finding an electron in your small volume dv, and how you find it? You just do r star multiplied by r. What is r star? R star is a complex conjugate of r. R will always be given to you. You never have to find r in the question. Okay, that I can assure you. So r is given here. You only have to do r star into r. So if you see r star here, do you think r star and r will be same for this function?
Yeah.
Because this
Yes,
is a
sir.
real function. Real function. If you do complex conjugate of 1, it is still 1.
The sign
If you
will
do
change.
complex, yeah, if you do complex conjugate of iota, it is minus iota. But for real functions, complex conjugate and the function itself is same. So we just have to square it. Now what is dv? That is very important because that is a source of many errors in the competitive exams. In spherical polar coordinates, you should remember that, you should know, you are an MSc student, dv is r square sine theta dr d theta d phi. Do you all know this? How many of you know this?
Yes, sir.
Yes, sir.
Perfect. So this is what I have written here. What people do is they put dr, simply dr. That is wrong. You are only taking the radial part, but in volume part, your theta also comes, phi also comes. Okay, because you are defining a small volume. Volume makes up the 3 parameters, not just 1 parameter. So this is your dv. Okay, now let's see some of the questions which can actually which can come. I will be discussing 3 questions. I have done the calculations. I will only be explaining the steps, and then you are good to go. Okay, after these 3 questions, I will be closing the session because these 3 questions will actually summarize everything which we have done today. So number 1 question is, your hydrogen atom is in ground state. So can you tell me what does ground state means? What is the N for ground?
N
What is
equal to
N
1,
for,
N equal to
and what is L?
0. Sorry, minus
0.
1. 0,
No,
sir.
L is 0. Okay, so 1 0. So your electron is in 1 0, and someone is asking you what is the probability of being between 0 to A. That A is a Bohr radius and nucleus. Now it's a very interesting question. If this, according to the Bohr model, if we believe in Bohr model, this is a nucleus and this is a nucleus and this is a first orbit. Between the nucleus and this orbit, can you find electron? Tell me.
No, sir.
No. Bohr model says no. Right? All agree?
Yes, sir.
This is a
Yes,
first
yes,
orbit, na? Electron is revolving. Okay. Now, according to the quantum model which I gave you, electron is a cloud. So it is a spherical cloud around it. Something like this. Just give me a second. I think drawing is not being visible to you. Okay. Just a moment. It will load. So according to the quantum mechanical picture, it is a cloud, spherical cloud around the nucleus. So if it's a spherical cloud around the nucleus, then you should be able to see you have a probability of finding an electron between nucleus and the first Bohr radius. With the image it will be more clear. Let it load. I think something internet problem is there. Yeah, can you see the image now?
Yes, sir.
Yeah.
So
Yes, sir.
within that distance only electron is also possible. So Bohr model is not actually a correct model to think in quantum mechanics. Now you know why. Okay, because Bohr model just assumes that in between nothing is there and the electron is in this circle. That's a very simplified model. In quantum mechanics it's not like that. And this sphere, what do you think? Where does the boundary of this sphere is? Is it ending at A? Means 0 to, if this radius is A, do you think this boundary is ending at A?
No, sir.
No, sir.
Okay, so why? Because if you see the function R10 function, where this function will actually become 0?
infinity.
Infinity. So your electron is still infinity. Your electron is still infinity. Okay, but practical limits is up. If you see 3 or 4 times A, it will go to 0, almost 0. Okay, in the practical case, but mathematically it goes to 0 at infinity. So both the pictures are quite different to imagine, and we have never been thought in terms of this this Schrodinger equation picture. So from now on till the time you are doing this quantum mechanics in 3D, think in this image. Now there is a probability that you do a measurement and you find an electron less than A also, or less than A also you can find. And there is a probability that you can actually even find the electron at R equals to 7A. This probability is very small, I agree, but there is still a probability. Okay, so that you should actually remember. So the question is how you find the probability, how much is the probability that I will find an electron between 0 to A. So how you do it? You do a probability density, you take a probability density function and integrate it from, so here it will be, sorry, here it will be dp, integration of dp from 0 to A. Okay, so you just square it and integrate it. Your R limit will be from 0 to A. Your theta limit will be from 0 to pi. Your phi limit will be from 0 to 2 pi. It's a basic spherical spherical polar coordinate system. You find this. Okay, you find this, you do this integral and you get some value. You don't have to worry what this value is. You only need to know how to do these calculations. I want you to repeat these calculations. The reason being, there are two mistakes which students commonly do in exams. Number one, they do a calculation mistake because integrals are confusing. Minus plus sign is confusing. Maybe I have done some mistake. You can correct my mistake. Okay. Second, when they start the problem, they don't consider the exact spherical polar coordinate systems. DV, they write DV wrong. That is a number 2 problem. So these two problems that you should avoid. No silly mistake will happen in the exam. Number 2 question. Find the most probable position. Okay, if your electron is in R21, means N is 2, L is 1. Then what is the most probable position where your electron will be? Okay, so number 1 mistake what students do is most probable. So what they start doing is R21 by dr should be 0. at R max. This is how we find the maximum minimus. Okay. Wherever there is a maximum, wherever there is a minima, take the derivative and bring it to 0. That point will be maximum or minimum. Okay. This is how you do maximum minima in general. Do you all agree? Right?
Yes, sir.
But should you do the derivative of R or actually probability?
Probability and then take its derivative.
Probability.
Yes. First you find the probability density, then take that derivative. Okay, because you are asking the where the probability is maximum. You are not asking where the radial part of the solution is maximum. So this is a mistake that students do. That's why I have added that question. So first we will find the probability density. Simply dp. Now in this dp, what students do? They do the square of this. Simply square. They don't add this term 4 pi r square dr. Okay, they don't add this thing. Then you do dp by dr. Okay, dp by dr, and then you make it to be 0, and then you will find that r maximum is 4a. You can do this calculation. There is not a very big problem in that. So you actually find that when your electron is in n equals to 2, l equals to 1, the probability where it is maximum probability where it can be found is at actually 4a. Okay, 4a. These kind of questions comes in gate, net, JEST, every part. Third question is very interesting and you can actually solve this. I have given the solution here, but I will like you to solve from the nodes. You have to find which of these 4 options is this R from the nodes. So you know the formula for nodes, L minus L minus 1. So what do you think will be the answer? Very quickly do it. There is one node here, this one, or is there any one more node? Is this is also a node or not? How many nodes are there?
One.
Okay, always
One.
remember we have to, yes, we have to consider the node between 0 and infinity. We do not need to consider 0 or infinity. So in between there is only one node. So which of these 4 satisfies that? Very
Option
quick.
A.
3 1.
Option A, 3 1, everyone, because 3 minus 1 is 1. All other will give you 0. So option A is correct. So now there is one problem which I have given. Okay, so you should try this. This is a Griffith problem. If you don't understand this problem, what you do, you see the Griffith solution. Very simple. So solve this problem. This will actually give you a very good idea. Very good idea. So whenever it is written, find the average R and R square for electron in the ground state of hydrogen. You can go and take the wave function for the ground state. Okay, in the book it has been mentioned. You can take from there. You don't have to drive it or something. Always in the problems, wave functions are given. So you can take that wave function and do all the calculations. See the solutions. If you don't understand how to do it, see the solutions, match your answers and get these all 3 parts done. With this, I think I will end the today's session. Tomorrow we will move to angular momentum and how we can represent it in matrix form and how the different problems from the angular momentum comes into play. So that we will do tomorrow. Okay, so today I hope you all understood the session, whatever we discuss. Okay, now I can take the question.